I would start by now by sharing my screen. Could someone please confirm that you can see my screen correctly using this presentation with the okay, cool. Well, hello and welcome everybody to our quantum leadership session. This is the fourth leadership session that QBN is holding this year, and today the focus topic will be on the quantum computing error correction. I am Zainab. I'm the quantum technology manager here at QBN, and I would like to thank you all for being here and also thank the Bayern Innovative Digitalisierung. They are our supporter by these meetings. Let me just go briefly through the meetings and a brief explanation and introduction about QBN, and then I will hand in the scene to our esteemed speakers. As said, I would start by a brief introduction about the QBN. After that, we will have some insightful talks from our three speakers. And this is something new for our leadership sessions. We will have a roundtable discussions, and Yuval Boger, the Chief Commercial Officer from the Quera Computing, will be moderating these discussions. So I really encourage you to start with us until the very last minutes of this meeting, and I can assure you that you will find it very fruitful and very interesting. Just before going on, there are some housekeeping requests to you saying that please change your name synthesis to full name and then in parentheses your company name. And by the Q&A session, when you want to ask your question, I encourage you to also turn on your camera, so it will give us more the feel to being in a in-person session, a meeting. This meeting will be live streamed and you can watch it on YouTube. It will be also recorded so you can watch it later on YouTube. The presentation from our speakers that you will see here will be available in our QBN portal. However, the presentations are only available to the QBN members, meaning that you have to log in with your account to our website and then you will have access to them. For the Q&A session, after each talk, you will have the options to use the hands up button. You can write your questions in the Q&A box on the below bar of your Zoom application. You can request for a mic opening, or you can write your question in the chat box of our YouTube streaming video. So let's go on what is QBN. Here at QBN, we have one mission, and that is build a resilient quantum economy together. And for this, we are the world's leading innovative networks and think tank for quantum technologies, meaning that we are dedicated to establishing quantum for good to tackle global and societal challenges. To achieve our goals, we have four main objectives. Starting with that, we want to serve as a platform for collaboration, intelligence, and business, because we want to provide access to an international network for you. And to do so, we would foster the dialogue between industry, science, and politics. This means that with this, we want to accelerate technology advancements, commercialization, and also industry adoptions. And finally, using all these, our main goal is to drive the growth and competitiveness of the quantum industry. We have been working so hard on our goals and our objectives, and here you see a list of our QBN members. All the members you see here, or the logos that you see here, are members that we gathered here together to help by building a better quantum industry together. Each logo that you see here, you can read about them and gain more info about them in our website. You just need to go to our website, and on the members, you will find these logos, and also you can search by name. You will see an explanation of what they do and what the goal of each of these members are. And I'm sure you will find very good connections there. But after seeing all these members, you might ask, so what are the benefits of being a member of QBN? The benefits are more than 7 steps for more than 7 points that you see here, but the main points are listed here for you. First of all, you can connect to business and collaboration partners from your entire value chain, because we do not focus on only a part of the value chain. We try to cover all parts of it, from hardware and software providers to the suppliers to researchers, developers, and also educators. And that's not only it. We would go with the investors, facilitators, and also end users. Beside the quantum leadership sessions, the one that we are here now, we have other QBN events. These meetings are for the members only, so invitation only for the members. And these are not only a online meeting, but also we have on-site meeting and also other services and joint activities for our members. This means that you can gain visibility and you can join international trade fairs by being a member, and for sure gain deep tech and market insight and exchange knowledge and experiences. This means that we can help you by getting fast access to private and public funding and business support among you. The ones who are QBN members have also benefited from this fast access to these fundings and business supports. And finally, to want to contribute, you can contribute to QBN's lobbying effort, road mapping, and governance. This one is running now, and we are getting a very good success in this way. QBN members are not only in Europe, we also have members from the whole world, from the United States, North America, and also Singapore, Japan, and also Australia. And as said, we do not only cover one part of the value chain. We try to cover all types and sizes. So from large corporates, SMEs and startups to research and technology organization, university facilities, and also labs, the government agencies, and also other companies. As a network, we are looking back to almost more than 4 years of success story. We have built more than 90 international members. We have now 6 technology working groups. We can check them on our website again, and you can see the vision and mission for each working groups. Our social media have more than 20K online reach, and wherever there is a global event on the quantum industry, you can for sure find us or our members there. Until now, we have initiated more than 100 partnerships and brokered more than 200 million investments. And that's not all. We also have a close relation with the government. In this way, we can support our members the best we can. And here, we can ask this question to us as QBN and also for all our members. And that's how can we do for each other? How can we build a connection to help each other to grow in this industry? And how can we together drive the quantum industry together? So if you are interested in the activities of QBN, the job openings, the news from the new QBN member, or the news in the quantum industry, upcoming events, and so many other things, I recommend to follow us on LinkedIn, X, and YouTube, or you can sign up to our QBN portal and sign up for our newsletter. So you will get access to latest news and anything that is happening in this industry. For this, I would stop sharing my screen, and I would thank you all for listening to me. Now I would like to ask Marcus. He's the university professor from the RWTH Aachen University and also Jülich Forschungszentrum. Marcus, the stage is yours. You can start sharing your screen and walk us through the dawn of quantum fault tolerance.
Thank you very much, Zainab, and welcome everybody. I'm really glad to have you, and thank you very much for having me here. I'm Markus Müller. I'm leading the Theoretical Quantum Technology Group at the University in Aachen and also at the Research Center in Jülich in Germany. And as Zainab said, I would like to take you on a tour into what I call the dawn of fault tolerance. I hope at the end of my short presentation, you'll be convinced that actually quantum error correction and useful error-corrected quantum computation is starting today and not in 20 years or so, what you sometimes hear. All right, if we then look a little bit ahead and really look at the applications for which we want quantum error-corrected quantum computers, for instance, in quantum chemistry, material science, or cryptography, for instance, what you see here is essentially a plot where you see that in order to run these useful algorithms for which we have essentially performance guarantees or very strong evidence that these will provide a quantum advantage if run on fault-tolerant quantum computers, we need on the order of millions or even billions of non-trivial logical gate operations here on at least a few hundred or 1,000 logical qubits. Yeah. And what you see here is essentially the current hardware, as we will be seeing also in later in my talk, roughly is operating on physical qubits with error rates of 10 to the minus 2, 10 to the minus 3. However, even with future improvements in the hardware, we will not get into this regime where we can essentially operate logical operations without error correction simply on bare physical qubits at these required error rates, which are the inverse. For instance, 10 to the minus 9, 10 to the minus 10 also, where we have to get into in order to be able to run these type of applications. And that is why I want to take you on a tour and leave a little bit the NISQ era of quantum computing behind, where we essentially have this mindset of running quantum applications, small-scale algorithms directly on physical hardware, perhaps doing a little bit of quantum error mitigation, error suppression, but rather to have this intermediate stack here where we do not run logical algorithms directly on physical qubits, but rather on so-called logical qubits that are equipped with quantum error correction capabilities. And what I will show you is how we can realize quantum error correction, but also quantum computation at the logical level as we know it all very well from physical qubits. So this brings me a bit to the outline of my talk. I would like to start with a very quick introduction to topological quantum error correcting code and what I call the quantum memory challenge of keeping logical states alive. And then the quantum processor challenge of how we can actually equip these systems with universal quantum computing capabilities. And then, time permitting, I will very briefly comment on different approaches to scale up the systems and some new ideas of how we can perhaps improve things by some other non-alternative approaches. All right. What are topological quantum error correction codes? The idea is to store information not in physical qubits, but in a collection and a many-body quantum system, as shown here, for instance, for this toric code. And the rough idea is that as long as noise that affects our physical qubits acts only locally and weakly enough, then we can protect the information by spreading it out globally in this many-body quantum system. Let's right away jump in, perhaps, into a concrete example and a project that we've been working on together with the group of Andreas Wallraff at ETH Zurich in Switzerland, who are building superconducting qubit-based quantum computers that you see here. On the left, you see the smallest example of a topological surface code, which is a planar version of the toric code I showed you a second ago, which is formed of 9 physical data qubits here shown in red. And then there are some helpers, some auxiliary qubits here shown in green and blue. And these qubits are being used to constantly and repeatedly measure the effect of errors that affect our physical qubits. So what one does is essentially, if an error happens on a physical qubit, one looks at correlations, and these are described by these so-called stabilizer operators that act on groups of physical qubits here. For instance, these 4-qubit operators here of X type or Z type and of X type to detect bit and phase flips. And what one sees by measuring these via these helper qubits is an error syndrome that gives us information which we can feed into decoders to make a guess of what most likely has happened on our system and thereby correct it. On the right, you see here a picture of an actual experimental superconducting chip with the 17 physical qubits, the surface 17, built from 9 data qubits and 8 ancillas, with the corresponding, flux lines and readout opportunities and coupling opportunities to realize gate operations, initialize and read out qubits. What one does then is, in order to run quantum error correction, one repeatedly measures this error syndrome by measuring these ancillary qubits, which are coupled to the data qubits here, being read out, and in parallel, one can then even map out the information of the other type of stabilizers in parallel. This information is then used in order to make a guess of what has happened and come up with a suitable correction. What you see here on the right then is how this works in practice, where you see here now for an initial encoded logical qubit here, in a certain logical state now, how this evolves under applying up to 16 rounds of repetitive quantum error correction. And what you see here is that in this experiment, the logical encoded information still decays. So even if you have quantum error correction, there will always be some residual errors. And in this experiment, the logical information still decays a little bit faster than it would decay if we store it in single physical qubits. So that is kind of close, but not yet at the break-even point for beneficial quantum error correction, but still a major achievement towards achieving or keeping a logical qubit alive. Very shortly afterwards, Google took one step further and increased the system size here, working with a distance 5, so-called surface 49 code. And what you see here on the right is then that by scaling the system up, they were for the first time able to show that the logical information lived for a little bit longer, and this is then encoded in just a smaller quantum error correcting code. And this is really kind of taking a first step into this regime where scaling up the system really provides increased protection of the encoded information. So an exciting step towards getting into this regime of beneficial quantum error correction. Later, as I guess we will hear also in this session by contributions from QERA, neutral atoms also looked at implementations of the surface code with even larger code distances, however, with no QEC cycles or repeated QEC cycles shown yet. All right, let me then change gears slightly and tell you a little bit about how we can not only keep quantum states alive, but actually do also logical quantum computation on our logical qubits. And this is what I call the quantum processor challenge. All right, before going into this, let me get one concept very briefly across that is very, very important, namely the concept of quantum fault tolerance, which is kind of an additional level on top of quantum error correction as a general concept. So the idea is we want to realize, for instance, encoding of information in a logical qubit as shown here, run quantum error correction cycles, do logical gates on our qubits, or even entangling gates between logical qubits, and finally read out our logical qubits at the end of a logical quantum computation. And now the challenge we are facing is that all the components in this circuit can be faulty. And what we have to make sure is that if a few errors occur, those do not propagate through the subsequent operations and spread in an uncontrolled way over the hardware. And this is what fault-tolerant circuit designs guarantees. So why is it so important to work with fault-tolerant circuit constructions? Imagine that you have, for instance, a single error, in the encoding process, and as long as this only propagates onto a single error on one logical qubit, for example, this will be picked up in the next round of error correction. So this is fault-tolerant. On the other hand, if you have a single error, for instance, in the logical gate that spreads onto, for example, 2 errors, and on a distance 3 code, which can only correct 1 error, then you see that this single error directly leads to a logical failure. So this is an example of a non-fault-tolerant implementation of a logical gadget. Now, if you work with non-fault-tolerant implementations, there will be always single error processes that will lead to a failure. On the other hand, if we work with fault-tolerant circuit designs, single errors are correctable. So at least 2 detrimental events have to happen in order to lead to a failure. And this leads to this quadratic scaling. And what this means is that this is essentially a guarantee that we theorists give to our experimental colleagues that if they work hard enough and get the physical error rate below certain thresholds, then they will get into this regime where the quadratic suppression of errors starts to set in, and they will start to outperform physical qubits. Now, how does fault-tolerant realization look in practice? You see this here for an example of doing now a logical C0 gate and entangling gate operation with one logical 7-qubit color code and a second qubit color code. And this can be done, this logical C0 gate, by doing pairwise physical C0 gates as is shown in this kind of pairwise way here. And why is this fault tolerant? Well, if a single error happens, as before, this error can still propagate, and infect, so to say, another qubit on the other code. But as you see, this will only result due to this construction in a single error on each of the codes. Again, this is correctable and will be picked up by the next round of error correction. Recently, we worked then together with the University of Innsbruck and experimental colleagues there on realizing some of these concepts in a trapped ion quantum computer, of which you see here a cartoon, where each of these points corresponds to a trapped calcium ion, encoding one physical qubit, which can then be operated by addressed laser beams in order to realize gate operations and also initialize and read out the qubits. And these systems now are living in this 19-inch racks and are no longer on kind of messy optical tables, if you like. If one has this transversal C0 gate at hand, this also opens another possibility to do a different type of quantum error correction, so-called Esteemed type error correction. And here the idea is that if we want to correct errors on one logical qubit, the upper logical qubit here, we can take an auxiliary logical qubit in a known state, say in 0, and then by realizing this C0 gate operation, the errors propagate from the upper to be corrected logical qubit onto this auxiliary qubit where it can be read out. And directly in single shot, this is fault tolerant, and we can take this information to come up with a suggestion for of how to correct these errors. If we now run this both for bit and phase flip errors, you see this kind of schematically shown here, where we repeat these rounds of X and Z type error correction over and over several rounds here for two Esteemed error corrected color codes. And what you see here is that this scheme then outperforms on the same system here a state-of-the-art flag qubit error correction. And this is the case despite kind of still quite noisy mid-circuit measurements that are needed here for this repeated Esteemed type of error correction. Okay, but what I wanted to talk about is not another way of doing error correction, but actually logical gates. So the nicest and simplest way to do logical gates is in this transversal way, which we have seen already for the C0. This also holds for single logical qubits, where, for instance, on color codes, you can do a logical Hadamard gate that prepares logical superpositions by simply doing a sequence of physical Hadamard gates. And this is fault tolerant by construction, because if something goes wrong on one of the physical gates, this will just result in a single correctable error on the logical qubits. However, the bad news is that in order to reach universality, for which we need a C0 gate to entangle logical qubits and a Hadamard and T gate to do arbitrary logical operations on single logical qubits, and there is no code that allows you to do this universal gate set in a transversal way. So that looks like a roadblock that has been known for a long time. And only very recently, people came up with new ideas of how one can use so-called flag qubits to prepare so-called magic states and inject them to realize this non-Clifford T gate, which is needed for universal programmability of the logical quantum processes. We adapted such a scheme and optimized it for a trapped ion setup, where you see here essentially a version where this magic state, of which you can think of a state on a Bloch sphere pointing in a kind of inclined direction here, is prepared. I don't want to go into the detail. The idea is here that one can fault tolerantly prepare and verify this preparation of this logical state with a very high fidelity of more than 99% logical fidelity. And after doing this, after fault tolerantly preparing this state with this flag paradigm rather than a magic state distillation, one can now take this state and teleport it onto a second logical qubit. And by doing this teleportation and teleporting this kind of inclined state, what one realizes is a 45-degree rotation about one of the axes of the Bloch sphere. And this is the T gate that we need. What you see on the right is the first experimental signature of such a logical T gate process matrix. There's another way I briefly want to comment on how we can actually realize universal computation, and that is by so-called fault tolerant code switching. So what is the idea there? The idea is if we have two different types of quantum error correcting codes, none of them offering a universal transversal gate set. For instance, 2D color codes of allowing the Hadamard, we can use a 3D color code allowing for a transversal T gate and switch information in between the two codes, so that when we want to run now kind of a logical computation, we can stay in one code when we need one gate, then fault tolerantly switch the information, the logical encode information, to another code in which we can do the other gate, and back and forth, so that in this way we can also reach a universality. And what we did there together, again, with the colleagues in Innsbruck very recently is to first of proof of principle demonstration of this concept here, switching between a slightly reduced version of a 10-qubit morphed color code and a 7-qubit Steen code in a fault-tolerant way. And what you see then is here, kind of in these results, is that you can reach then kind of more and more densely arbitrary points on the logical block sphere by combining Hadamard and T-gate, and this is really the signature of this universal control on single logical qubits. One can then go one step further and also use this in a slightly more complex quantum algorithms, for instance, on 2 logical qubits. And here you see a scheme in which on a single logical qubit, after switching, one now can couple and tangle this with a second logical qubit here, and then prepare here for different input states, different entangled logical states, which are no longer non-stabilizer states, but which can only be reached really if we combine all the gates from our universal set of HT and C0. And this is really exciting because it's really the first time in any architecture that a universal and fault-tolerant logical gate set has been shown here. And what this kind of shows is that we are now entering the era when we can really think about running logical quantum computations on logical qubits and in principle in a freely programmable universal way. Okay, let me then in the remaining minute or so, if I may, very quickly conclude on mentioning 2 other approaches that I find very exciting. And one is so-called measurement-free, but still fault-tolerant quantum error correction. And here the idea or motivation is that measurements in many architectures are either slow, technologically challenging, or they might even be destructive and lead to loss of atomic qubits, for example, in a measurement. So the question is, can we get rid of these measurements completely and simply kind of run a autonomous but still fault-tolerant open system dynamics, coupling our data qubits to some environmental qubits, so that even if this is noisy, we can still correct errors and maintain information? And the answer is yes, this works. And I just want to advertise, that if you want to look into kind of more details of this, we have a very recent publication on this approach here, which was featured in Physics. The idea is, again, to have a logical qubit that has to be corrected. It's coupled in a kind of a bit more involved way onto an auxiliary system, and then it's constructed in a way that we have only quantum feedback, only reset of operations, no measurements at all at any stage, in order to kind of, in this quantum feedback way, correct the errors on our hardware without the kind of external intervention in an autonomous way. And we've worked out protocols of how this can be implemented in neutral atom arrays that we'll hear about more later in this session, and also come up recently in collaboration with Planck QC, a startup from the Munich Quantum Valley, where I'm working as an advisor on even further optimized measurement-free versions for neutral atoms. Finally, of course, we want to scale systems up, and there we are working together again with theory and experimental colleagues. For instance, in this entangled logical qubit program financed by the US, and also in some European projects like the Quantum Flagship, on coupling now several logical qubits, increasing their size in order to come up eventually, with a scalable quantum computing architecture with more and more logical qubits based on various physical systems, such as superconducting qubits here or trapped ions, for example. And then the last slide, just to advertise kind of a new approach, again, from the area of trapped ions. There's a new type of ion trap design that was that we explored together with the University of Innsbruck, which we call the quantum spring array, which is kind of pictorially shown here. But the idea is you have linear ion strings where you have full all-to-all connectivity, which is the kind of the characteristic nice feature of trapped ions. And then these ion strings can be kind of moved in both directions in a 2-dimensional architecture. And this is really an ideally suited architecture for scalable embedding of quantum error correction schemes, as I've shown you. And it allows transport without splitting and merging, which is the kind of standard approach, for instance, followed by continuum in order to scale up systems. All right. Let me then conclude by saying that there's many more challenges, like developing new codes. Let me skip this in the interest of time. If you're interested, we have nice new protocols on so-called quantum LDPC codes, which allow you to use your precious physical qubits to have better protected and more logical qubits. And kind of conclude with this, I hope that I could give you, by this very short and quick tour, a bit of an idea that the NISQ era, in my opinion, is coming kind of slowly to an end, and we entering this era where we start now to think about quantum computing really on logical qubits. However, this is, of course, not the end of the story. There are many interesting open key challenges that I just want to list here briefly. If you're interested in joining this endeavor, please get in touch. And yeah, with that, I hope that I convinced you that fault-tolerant quantum computing is starting today, and it's even starting to become useful today. With that, thank you very much to my group and the funding agencies that support our work. And thank you also to my QC collaborators, and thanks very much for your attention.
Thank you very much, Marcus, for a very interesting presentation. I do have a couple of questions I wanted to ask you before we start with the next presentation, please.
Sure.
You presented a slide showing where we are today and what's needed to run truly useful algorithms. If you had to estimate, how far are we away in years or decades from that happening?
Well, I mean, I don't think we are so far away. I think, we have already kind of ion systems of limited size, shown universality. I think you, of course, or neutral atoms, let's say more generally, will probably also pretty shortly get into universal logical operation of quantum processors. And I think, we will see on the next perhaps few years, years, see the first interesting applications. I see them more on the scientifically interesting side. For instance, digital quantum simulation of many-body physics, I think, will be one of the first interesting applications. And then, until we really get into the regime of, quantum cryptography or quantum chemistry, this will take some more years. But I would say definitely less than 20 years, but I don't want to kind of nail down a number more precisely.
You mentioned several schemes that do require measurement. I mean, at the end, you mentioned a measurement-free approach. But
Yes.
Those that do require measurement, I suspect this is a classical measurement. How do you see that happening? Is that with a GPU, an FPGA, something else? Is that a challenge today?
Sorry, you were cut up in the middle of the question. You said there is a measurement happening?
When there is measurement happening, it is
Yes.
typically processed by classical computing. Is that a challenge today? Do you see that happening with an ASIC, with a GPU? What are the architectures that you see for actually performing the correction?
Okay, so I mean, kind of to be clear, perhaps to highlight this, I was very, very quick here on this. In the measurement-free error correction scheme, there's really no measurements happening. I mean, of course, at the end of quantum computation, you have to read out your qubits, but at the QC cycle, there's no measurements. So this is fully autonomous, which also means that there's no kind of classical processing of information. And at the moment, we are looking into, to which extent one can scale this up, for instance, by ideas of concatenation and so on. And this has to be seen whether, how far one can scale this up, or whether this measurement-free protocols might be kind of more a low-level scheme, and based on which we operate some low-level, small quantum-corrected logical qubits, from which we then build in a standard way, for instance, then more robust logical qubits. But then you're right, in the standard scheme of quantum error correction, of course, you constantly read out the ancillas. And indeed, it's a challenge to do this quickly enough, and also to process the information quickly enough in decoders. And I think there it depends a little bit on the platforms. So kind of, if you have a fast platform such as superconducting qubits, then you have to be fast. If you're working with atomic systems, then typically you have a little bit more time to process this classical information. And my view on this is that there will be certain basic type of decoding tasks that will be probably done at a very low local hardware level. Basic corrections, perhaps, feeding in a missing atom, adapting some stabilizer readout, things like that. But then some higher level logic will also be needed when we think about, in sequence decision logic, which is necessarily required when you want to run, for instance, non-Clifford operations by magic state injection and the like. Yeah. So that these measurements and the respective kind of electronic and classical control will probably take place at different levels. Yeah.
In my last question for now, before we move on to Annette's presentation, obviously we'll have lots of time for discussion later. You mentioned work that you've seen or that you're doing on superconducting qubits, on trapped ions. You mentioned that you're advising a neutral atom company. Yeah. If you had to choose one modality, what would you choose? If someone forced you to choose a modality, what would you do?
Well, I guess that you and Sheng Tao will probably convince us that we should be excited about the neutral atom progress, which I think is very fascinating progress. I also see some challenges there in the midterm where one has to see, you know, in terms of speed, in terms of, you know, really large scale scalability that we can probably discuss a bit later. I think, to be honest, the race is open. I like to work on all the platforms a lot because the challenges are different, you know, because the capabilities are different. And then as a theorist, I like to think about how to getting around. Yeah. Certainly, I would say, you know, perhaps it's a fair summary that trapped ions and superconducting qubits have been kind of in the lead for quite some time, and now the Rydbergs have been showing very exciting progress on an impressive number of logical qubits. And yeah,
very good. Thank you very much for the diplomatic answer.
Yeah.
Annette, we would love to hear your presentation if you can.
All right, thank you. Let me just try and share the correct screen. All right, do you all see the slides on my mouse? Just checking.
Yes, okay.
Yeah. Okay, perfect, cool. Then, yeah, thanks for having me here today. So I'll talk a little bit also on more of like an alternative for more near-term quantum error correction, which is a recent work at Parity QC, where we try to use the error correction capabilities of the Parity architecture together with some other code, in particular with noise-biased qubits, like, for example, CAT qubits, to obtain, in the end, the quantum error correction code with fully fault-tolerant protection and fault-tolerant gates. And as is probably not that well known yet in the context of quantum error correction, I will also start with a bit of an introduction of what I actually mean when I say the Parity code or the Parity architecture, and hopefully also be able to show you that or how we can use this code not only for error correction, but also for an easier implementation of many logical multi-qubit gates. So to start, consider just a bunch of qubits between which we want to implement entangling gates, ideally in parallel. And in order to do this, let's say we're allowed to add additional qubits to our system. So if we want to implement an interaction between two of our qubits, what we choose is we add one new qubit. We label this with the 0, 1, by which we mean that we want to be able now to implement a kind of logical interaction between these two original qubits, 0 and 1, in the ZZ basis, by actually only performing a single physical operation, also a Z operation, on this new qubit. Now, how can we make this come true? Because right now it's just wishful thinking, but we can actually realize this by just adding a stabilizer and requiring the system to be in the +1 eigenstate of this operation in this case. And what does this do? In this case, it's just a product of the physical Z operations on these 3 qubits, which we require to act kind of as the identity on our code state, which means in turn that then, of course, a physical Z on this new qubit acts exactly the same as the product of these 2 other Z operations, just to end up at the identity if we multiply them all together. Or if we look at this a little bit differently, if we just keep this definition of our original qubit saying my logical set is still just a Z here, and my logical set 1 is still a Z here, then actually in terms of eigenstates, this new qubit here now just represents the parity of the 2 logical qubits, which are still kind of encoded here, which is why we call the whole thing parity code. And you can, of course, add much more qubits than just a single one. For example, in a single layer of adding new stabilizers and qubits, we can get a lot of parity qubits, all allowing us to implement some kind of nearest neighbor interactions of the original qubits. But then with more and more layers, we can in fact actually get all different combinations of logical qubits on one parity qubit somewhere. And we still only need these kind of local stabilizers to do this. And this is then what I actually mean by this parity code. So in the end, it's just a classical stabilizer code, classical because all of these stabilizer operations are just Z products. But the main difference now to other stabilizer codes, I would say, is that we have constructed this code not primarily with the error correction capabilities in mind, but actually just with this resulting mapping from physical to logical operations that will allow us to easily and also in a parallel manner implement a lot of many-body gates on the logical qubits. So talking about gates, let's also maybe try to get a full gate set onto this new code that we've created. So as I've shown, we have the definitions of logical Pauli Z operators already directly from the labels that we've put on this qubit. So single body logical set, we can just keep on these original qubits that we started with, and the multi-body we have in the parity qubits. And yeah, the main point is that, of course, all of these things are now actually much easier in the code than they were originally on the qubits. For Pauli X operations, of course, then the whole thing is the opposite. So logical X gates get actually harder in such a code, because in order to flip a single logical bit here, I actually need to flip all of the qubits that contain some information about this logical qubit, either in terms of a parity or directly. So for example, this would be all the qubits I need to flip if I want to do logical X0, because it's just all the qubits with a 0 in it, and so on. So I can just construct my logical X operators like this. This is, of course, a little bit harder to do, but actually that can also be a good thing, because, I mean, even though that wasn't our original intent, we can, of course, use this now also for error correction, because it's still stabilizer code, so why not also use its error correction capabilities? First thing we see there, of course, is I only have Z operators as stabilizers, so I can only get bit flip error correction. But it's a start, I'd say. I'll come later to how we want to make this fully fault tolerant. In terms of bit flip error correction, this kind of triangle layout that I've shown so far actually has some interesting property, namely the code distance, so the smallest number of qubits that I need to flip together to get to a different valid logical state, in this case, scales exactly with the logical system size. Because if I would add another logical qubit here, I would make each of these lines also longer by 1. So as bigger my logical system gets, the bigger in a sense also the error correction gets. Another interesting thing to observe is that compared to repetition code, which is maybe the most well-known classical error correction code, we actually only need half as many physical qubits, because each of these parity qubits now kind of acts to repeat 2 different logical qubits instead of just 1 per logical qubit. So in the end, we need only half as many additional qubits to actually get higher code distance than in the repetition code. Right, let me just quickly also show you what else is possible, because this triangle layout that I've shown so far is quite nice for all-to-all connectivity, but in principle, any other layout is also possible depending what you need in your algorithm. You can, for example, you can just cut off the tip of this triangle if you don't need these parity qubits, or if you don't need such a high code distance. You could also even remove some of these qubits with single labels. You could put different stabilizers here. If I put, instead of a triangle, if I add a square, I even get this kind of 3-body parity qubit on which now I could implement a logical 3-body interaction. And you can also combine this with ideas of repetition codes by just repeating some qubits multiple times and adding 2-body stabilizers between them. So in effect, you could even see the repetition code as a special case of such a bigger arbitrary parity code. And in general, we've recently shown actually that for any parity qubit or any group of parity qubits that you might want, you can actually always find some layout of these local 3- or 4-body operators as stabilizers that will put you this parity qubit somewhere in the code. So in fact, you can pretty much have arbitrary logical connectivity if you have enough physical qubits to use. Another aspect that makes such codes quite useful is also the ability to switch between one encoding and another. For example, if I want different parity qubits at a different step of the algorithm. And these kind of codes can be actually changed to each other quite easily, either with CNOT gates. I'm not going to go too much into details. The way that we prefer now is to use measurements. This is actually also very similar to the surface code. Maybe I can show the most intuitive thing, which is if I want to add a new parity qubit to an existing code, because I decide I want this new interaction now, I want to implement this in my next step, all you need to do is actually just implement a new qubit in the plus state and then perform a stabilizer measurement. So you find some stabilizer that links the new qubit. In this case, the new qubit will be 1, 2, 3. So I find a stabilizer that links it to 1, 2, and 3, for example. I perform my stabilizer measurement, and if the outcome is minus, well, I just flip the new qubit, and then the stabilizer should be okay, And then this will also be part of the stabilizer measurement, the stabilizer code. This kind of stabilizer measurement that I need to do, you can, for example, do on an ancilla qubit. Typically, I would say this can be placed just in the center of these plaquettes here, for example, like in this layout. So if you do this, we will always only need CNOT gates, physical connectivity between these measurement qubits and any of these code qubits. So the whole thing can still be implemented on just the square lattice connectivity chip. Right, but now let's get to the actual interesting part. So we want to take the whole thing one step further now and construct an actual fully fault-tolerant quantum computing scheme. And the way we do this is now to take cat qubits. So just to remind you, we've so far only have had a code that only has Z stabilizers, so we can only correct bit flip errors. In order to get fully fault-tolerant, we therefore also need something to protect against phase flips. And a very convenient choice to suppress phase flip errors, which we explored in a recent work of ours now, is this cat code. So the cat code or cat qubit is just a way of implementing a qubit or encoding a qubit in the bosonic degrees of freedom of a harmonic oscillator. So you just pick a coherent state alpha, say, and another coherent state minus alpha, make alpha big enough. And then you have two different states that are almost orthogonal, and you could just call this a qubit. What we do here, actually, instead of defining the alpha and minus alpha states to be the computational states 0 and 1, we actually define them to be the plus and the minus state of the cat qubit. And that's because in the cat qubits, these two states are exactly the ones which can be well separated from each other and between which we can actually suppress flips from one to the other by some proper engineering of the resonator. So if we use this definition, we suppress exactly these flips between plus and minus, which are exactly the phase flips that we don't want. And the nice thing of this cat code is actually that these phase flips now can be suppressed exponentially strong at the expense of only linearly increasing the bit flip rate, which we can then take care, for example, of with the parity code that we have. And another very important feature that actually also a lot of other hardware platforms with bias noise don't show yet is that in the cat code, we have a lot of bias preserving gates. So gates that even if the error happens during or maybe before the gate, in the end, it still is one of those errors that I'm allowing to happen, and I never get one of the errors I want to suppress. And in the cat code, we have quite a large gate set with these properties. For example, we have a Z flip, we have an X rotation, and we also have a couple of controlled gates, like, for example, the CNOT, which will come in very handy. Because now we want to, of course, put these two things together. So let's just consider this original layout again of the parity code, just that now each of these blue qubits is a cat qubit from the cat code. So we have like different resonators for each of these qubits. And now to get logical gates, let's just try to use these physical gates we have. So for example, from a Z flip on a cat qubit, I can directly get a logical Z flip if I do it on one of these qubits, or I could also do a physical Z flip on a parity qubit, then I just get two logical Z flips on the two different qubits in the label. It's not really entangling it, but I mean, it's something, it's a start. But more interesting is the CNOT gate, of course, because we can use these physical CNOT gates between cat qubits now to build a transversal logical CNOT gate also in the parity code. The idea here is just that the target side of the CNOT can be kind of treated like an X operation. So we just need to target each of the qubits in the logical targets X operator, and the control acts like a Z. So here we just need the logical control qubit as a label of all of these control qubits. I've shown these here now multiple times copied, just so that the whole thing is transversal, so that each of these CNOT gates can control from a different qubit, and we keep our fault tolerance in this whole construction. Right, but the actually interesting thing we want to do now, of course, is we want to use these parity qubits for what we've defined them, which is this mapping from single body set to many body set. So in order to actually get an entangling gate, what I want to do is to do some smaller rotation on a parity qubit, because that then would give me the effect of this many body RZZ gate between the logical qubits. Problem here now, of course, is that a small X rotation or the arbitrary angle Z rotation, sorry, Z, is actually the one thing that's not available in cat qubits in this construction that we chose, because this is exactly a non-bias preserving gate. So we need something else. Luckily, there is a solution, which is the solution that a lot of fault-tolerant codes come back to in the end, which is magic state distillation and injection. I know we've heard it's not the most efficient thing, but actually for cat qubits in a repetition code, there actually exists a very efficient scheme for the creation of high-fidelity magic states, particularly for the S and the T gates. So we can use this scheme. We just prepare the magic state on some kind of repetition encoded state, and then we teleport it onto our system. But the important point is we don't teleport it onto a logical qubit like is usually done. But now, because we still want to make use of these properties of this parity qubit, we actually want to teleport it somehow onto the parity qubit, which is a physical qubit. So we still want to do this fault tolerantly. So all we do actually is just we repeat this physical qubit a couple of times. It'll just look like the parity qubit itself is in a bit of a repetition code, but you can also just interpret the whole thing as a larger parity code. And then we can teleport it into this kind of encoded parity qubit. But once we're done, we can also remove all those copies again, and we will end up with exactly the small Z rotation on the parity qubit, which then will have this logical multi-body effect that we wanted. So, okay, I see I'm running out of time, but then maybe just quickly to show you what is possible. So with an S gate on a parity qubit, I can get this. This is actually the maximally entangling gate between the two logical qubits. It's also related to a control Z gate. So if I just add some more S gates to these single labeled gates, I get exactly a logical control Z gate. But of course, I can also, for example, if I teleport a T gate, I can get something non-Clifford. On the most general case, if I have arbitrary parity qubit, I can get like arbitrarily high order interactions, whichever angle here I can teleport into my qubit. So with that, yes, I'd like to wrap up. So I hope I could show you that the parity code or the parity architecture is really just a strategy for constructing efficient classical LDPC codes. So with like low qubit overhead, but most importantly, with really easy logical many-body gates that also can all be parallelized by just addressing different parity qubits at the same time. And also, I hope I could show you that it's also easily combinable with other codes, like, for example, the CAT code, which we've explored in this work. So, yeah, thank you.
Thank you very much,
so
Anette.
Yeah, before going on, I just wanted to thank you, Anette, and again mention that for our audience and who have question, you can write your question again in the Q&A box, or raise the hands up button, use the hands up button, or just open your mic and ask the questions. You can go on.
Of course, thank you, Anette. Could you tell me a little bit about Parity QC? What is it that the company does? I mean, besides fascinating research.
Yeah, I mean, it's moving quite quickly. So originally, everything we did was about optimization problems. So this whole mapping, this whole introducing parity qubits was exactly because in quantum optimization, it's exactly these Z many-body operations that we need. And it's kind of really slowly transitioned by just us realizing, oh, but actually it's just a stabilizer code, so we can use it for error correction. So now I would say we do everything. I mean, everything that really tries to implement certain algorithms in a most efficient way on certain hardware with whatever connectivity restrictions or gate sets they have. So this is now like our first endeavor into the error correction world, where we want to see also how much we can do on that side.
So just so I understand, it sounds like you could do one of two things, or maybe both. One is if I have an algorithm that I want to execute optimally on a given hardware platform, then you could help me realize that algorithm on the hardware platform. And the second thing potentially is that you can work with hardware vendors to implement efficient quantum error correction codes. Do I understand it correctly?
Yes, yeah, in a sense, it's really in both directions, because in the end, you need to know both, right? You need to know the algorithm and the hardware to actually find something that works.
Now, you mentioned your work on cat qubits. Not everyone does cat qubits. So what can you offer for people who do superconducting or ion traps, for instance?
So I mean, this is not really developed fully yet, but if you're talking error correction, of course, this whole architecture can also be supplemented just with a repetition code or another classical encoding that then you can, like, you could use a non-noise biased platform as the basis and then use one error correction code and one basis and then use this on top of that. I mean, in principle, you can even use it also on top of a surface code, maybe a asymmetric surface code if you still want to use a little bit these error correction capabilities. So it's really not limited to CAD qubits. It's just like a first attempt also to maybe more near-term applications, because these qubits already have these properties in them and you don't need to have an additional qubit overhead.
And speaking of near-term applications, there's a lot of work on error suppression and error mitigation and things that are not directly related to quantum error correction. Do you see these as long-term solutions? Do you see these as being helpful? Or do you think they will come and go?
I mean, I wouldn't say they are the long-term solutions, of course, but they're certainly helpful. Like even in quantum optimization, we see that even if we implement this non-error corrected, we can use these constraints and additional knowledge to do some error mitigation. And I think also if you have full error correction, it can't hurt to use everything you have to do even additional mitigation. So I'd say, why not? I'm sure it can always help.
Very good. I think in the interest of time, perhaps Shengtao, you could present now, and then we'll go back to the panel for additional discussion.
Great. I assume you can all see my screen.
Right.
Thank you for having me today. It's a pleasure to join this event. My name is Shengtao Wang. I'm the head of quantum algorithm applications at Quora. So as part of my group, we develop new algorithm and applications for both near-term quantum computing devices based on neutral atoms and also long-term QC architecture as well. So as part of my group, we do QC research and also co-design the QC code on neutral atom hardware as well. So for today, I'm going to tell you a bit about some of the recent work Quora and also our close collaborators from Harvard, MIT, and other collaborators did recently. So my first slide is actually very similar to Marcus' slide. So we all agree quantum error correction is a key element for large-scale quantum computation. As we know, the big challenge for large-scale quantum error correction, large-scale quantum computation, is that the error rate is very high now. So the physical error rate today is around 10 to the minus 2. And if we really push and on the physical level, the physical error rate can probably reach around the level 10 to the minus 3 for entangling gates. But there's a big gap between what we want to go. So to implement this large scale quantum computation that requires an error rate of 10 to the minus 15. How do we achieve that? And the answer, of course, is quantum error correction. And with quantum error correction, we'll be able to bridge this gap and encode many physical qubits into logical qubits, at the same time suppressing the logical error rate. So I don't need to tell you too much about what is quantum error correction, but just to set us on the same page. So the idea of a quantum error correction is similar to classical error correction, but of course, quantum error correction is more challenging because of a different basis, different error as well in different bases. So if we have supposedly n physical qubits, we can encode that into a smaller number of logical qubits. In this case, k number of logical qubits. With this encoding, the logical information is spread out in physical qubit, and we'll be able to protect physical errors. And that means there's also a co-distance between the logical qubits where this is error correction power, how many errors we need to incur in this logical qubit space to be able to create a logical qubit error. So with this, there's overhead in terms of encoding physical qubits into logical qubits. This rate of encoding number of logical qubits that we can encode divided by the number of physical qubits is an important number we need to optimize in quantum error correction code. Yeah, so moving on, and I will tell you a bit about neutral atom architecture and what are the advantages of neutral atom platforms in terms of error correction code and advancing the frontiers of quantum error correction as well. So, of course, neutral atom platform, we have neutral atoms as a main qubits, and one of the few key elements we have is this qubit shuttling architecture, where we can move the qubits and move the atoms during the circuit, and that means we can realize long-range connectivities and entangle the qubits far away. And we have this parallel operation that's also enabling by this qubit shuttling capability. We can move many qubits in parallel. We can implement many operations in parallel as well. And with this capability, we also design new architecture for neutral atom platform as well. One architecture is this zone architecture. I will tell you more about on the next page. And this really kind of enable kind of a processing and parallel operation in many levels as well. Yeah, so the zone architecture is very much resembling a classical computing mode. This is, if you know about classical computer architecture, this is very much resemble von Neumann architecture. So we have a storage zone that we can store our physical qubits and even logical qubits. And we have an entangling zone. We can efficiently entangle the qubits and do parallel operations on many different logical qubits and physical qubits as well. And we can have a readout zone that we have measure many qubits at the same time and then feed forward for future error correction as well. So this is a picture from one of the recent work from Harvard and in collaboration with Quora and other collaborators. This designing logical qubit architecture, which I will tell you more about this architecture later. But this zone architecture is really what enable a lot of advancement in this neutral atom platforms. So with this architecture, we can see that coupled with qubit shuttling, which you can see from this video here, there's a lot of flexibility in this architecture. You can design different ways of layout the qubits. You can design different ways of entangling the qubit different zone as well. This is a picture of implementing a physical circuits, actually. So this is up to 66 qubits, the quantum circuits implementing an Ising model, Hamiltonian simulation. And we can see there's actual images of atoms and qubits. We can move the qubits and from different zones and entangling them in the entangling zone and then move them back. This can create long-range connectivity. It can be also a test bed for early empirical tests for quantum error correction code as well. Since you can see there's a lot of flexibility in the architecture. One thing worth emphasize is that we have very few control lines that we need in this architecture. Since we move many atoms in parallel, we can use, for example, one control line to move one row of atoms in parallel. And we can use one global beam to entangle the qubits, pairwise entanglement in this case. And that can efficiently implement entangling gates on many pairs of qubits. So with this very few control line, that's also enabled this highly parallel operations and also make sure we can easily scale up the system as well. Another point worth mentioning is also we can implement considering multi-qubit gates as well, since this neutral atom system entangled by a proximity, and where we entangle the qubits by putting them together and excite them to the rebirth state. And that can naturally implement multi-qubit gates beyond 2-qubit gate, like 3-qubit Toffoli gate and other multi-qubit gates as well. That also will be a test platform for different error correction code as well. Great. And you can also see easily that with this, we can consider we have one block of logical qubits and another block of logical qubits. We can easily move them together and lay them on top of each other and implementing this transversal entangling gates. And there's a lot of advantage of transversal entangling gates, which some of this Marcus also mentioned in his earlier talk. Great. So with all of these key features assembled together, this is one of the recent work, as I mentioned, done at Harvard, led by Harvard and in collaboration with Quora, MIT, and UMD and NIST. And to implement this first and early logical quantum processor with neutral atom systems. In this work, you can find out on Nature paper here, there's a various of different error correction code we implemented. For the traditional surface code, which will be the standard error correction code, we implement surface code scaling up the distance from D to 3 to up to D to 7, and observing logical error suppression in scaling up the error correction distance. We also implemented different error correction code like color code and with breaking even fidelities, and up to 40 color code qubits as well, and creating logical GAC state on this color codes, logical color codes as well. And a different code we use is this 832 code block. And with this collaboration, we implement up to 48 logical qubits with many logical 2-qubit gates and even 3 logical 3-qubit gates as well. So this is one of the largest number of logical qubits one implemented so far. Just to give you an idea of what it looks like, this is the algorithm for this sampling algorithm on up to 48 logical qubits. You can see, as I mentioned, a lot of this is enabled by highly parallel operations. We have an entangling zone here. We move qubits in parallel and entangling them with this. If you see a red dot, that means entangling the qubits with a lot of parallel and also transversal gate implementation as well, since with this parallel operation, transversal gates are highly desirable as well. Great. So this is one of the recent development, between Harvard, Quora, and collaborators. One of the challenge where some of this the community asks is, we know neutral atom is very flexible and very scalable, but neutral atoms are slow compared to superconducting qubits. This is true, on the physical level. Our measurement, time scale is around 100 microsecond, and our shuttling time scale is also around 100 microsecond. That means to do gates, and that requires on the scale of time 100 microsecond. So for large scale quantum algorithms, for some of the applications in chemistry and others that require a long time to really run these large scale algorithms. And we're happy to report that with one of the recent work, which this work just posted on arXiv last week, we developed a new fault tolerance schemes to do fast quantum computing. And with this, we actually will be able to dramatically scale down the time, and this is also competitive with other platforms as well. Scaling, if we need a year to run our original circuits, and now we actually only just need a few days, and scaling reduction of 10 to 100 times. So what do we do in this work? And we developed a new fault tolerance scheme we called algorithmic fault tolerance that achieves a factor of D speed up relative to conventional fault tolerance methods. So this D is just to mention that again, this D is a codistance. So we know this D, if we need large algorithm to implement, D is always typically in the range of 10 to 100. So that means we can achieve 10 to 100 speed up for this reconfigurable quantum computing architecture. Of course, neutral atom is one of the platforms that we can move the qubits, and trapped ion system as well. That shows also you can move the qubits during some of the mid circuit as well. And so how do we achieve this speed up? This delve into a little of error correction, actual error correction schemes. In conventional fault tolerance schemes, we typically need D syndrome extraction runs per operation. To make this each part fault tolerance, we typically need D runs of error fraction here. And D is typically in the range of 30 for large algorithms. But with the new scheme, we instead of maintaining fault tolerance in each of this component, we consider the algorithm as a whole and do correlated decoding as a whole as well. So with this, we are able to reduce the D round of error fraction to a single round or constant round. And this will achieve a factor of D or more speed up. And we also show that this holds true for universal quantum computation as well. It's not only for Clifford gate, we can also do for T gates and for universal computation as well. Some of this is inspired by earlier works, which we did correlated decoding for this transversal architecture during this collaboration between Harvard, Clara, and Chicago. Great. So what are the main challenges to achieve that, and how do we resolve that? And to be able to do this error correction as a whole algorithm at the whole algorithm level, one of the challenges, if we measure part of the system in the middle and we feed forward, and we don't have the information of the whole measurement, the later measurements as well, and this can create challenges because we don't have syndrome information on other and measure qubits. The partial decoding result can give us a wrong correction feed forward if we don't have all the information of the other measurement schemes yet. So we solve this problem by adding another error correction round. So first of all, we do this partial decoding, which we only have partial informations. And when we reach other part of error correction, where we do this full decoding, we realize there might be some inconsistency of error correction interpretation with prior partial decoding result. And we show and also prove that with another layer of just purely a software layer, actually, we can reinterpret this measurement result and make sure the partial decoding result is consistent with full decoding as well. And this will be able to make sure we will be consistent throughout the error correction round for the full algorithm development as well. There's much more details in the proof and detailed implementation. We'll now have a time to go through it. So just to quickly show a result of this work, and we will compare where this algorithmic fault tolerance with a typical standard conventional error correction. With our algorithm fault tolerance scheme, we rely on transversal architecture, actually, which I forgot to mention earlier. With this transversal architecture, and that with correlated decoding, we are able to achieve this D factor speed up. And if we compare with the standard lattice surgery implementations on service code, we can see if we only implement one round error correction at each layer, and for transversal architecture and for our scheme, we can see error suppression as we increase the code distance. But for standard conventional lattice surgery, we are now able to show that error continue to depress with the code distance. This is only one round error correction at each error correction step. Of course, we do D round lattice surgery, we're able to suppress. And this really shows that the transversal architecture has a lot of advantage, and also this algorithm fault tolerance scheme really works in this case. So with that, I'd like to quickly conclude and summarize my talk. So I showed you neutral atom architecture. There's a lot of unique features for the system, and how that can help us design new and different quantum error correction code and new QEC architecture. And I tell you a bit about this, the recent work on logical quantum processor and this algorithm fault tolerance scheme we recently come up in theory. And there's other works, of course, in QLDPXC code and other novel codes that one can think about implementing a neutral atom system as well. So with that, yeah, I'd like to thank everyone for listening.
Thank you very much, Xiangtao. A few points of clarification, if I may. You showed the slide with the one of the algorithms implemented with the animation. Is that a video, or is that just a computer-generated animation?
Yeah, thank you for the question, Yuval. This is an actual system. This is every every pixel here is an actual atom we image. Of course, this is slowed down significantly to show an actual video. So this is an actual algorithm we implement on the hardware.
When Marcus was presenting his slides, he showed sequential operations between each physical qubit and a logical qubit, whereas you're presenting that we can do parallel operations. I mean, it sounds like that might be useful, but how important is it to do parallel operations as opposed to just one after the other?
Yeah, thank you for the question again. So this parallel operation is really a key element that enable a lot of this advancement for multiple reasons. One is, it's more efficient, it's time efficient. We can implement many of the gates in parallel. We don't need to do them sequentially. That has a time saving. And this is even more true for logical qubits. On the logical level, we typically implement on the logical code block, we can move the whole code block in parallel and doing transversal gates on two code blocks. And another big reason that has advantage is also with this parallel operation, we don't need as number of qubits as number of controls. So with 300 qubits here, we only need a number of control lines around 10 here. So that's really efficient. That tells us if we scale up the number of qubits, if you have millions of qubits, we don't want to have millions of control lines, just like our computer screen. We don't have millions of control signals behind our screen. So that will really enable scaling up as well, these parallel operations.
But it seems that one disadvantage here with this zoned architecture and the readout zone is that if you move ancilla qubits, or if you move qubits into the readout zone and then measure them, then they're kind of gone. If you're implementing error correction and superconducting, the qubits are there, you can reset their state and you can use them again. So how would one do a large scale algorithm if these qubits are gone?
Yes. So that's also a question a lot of people ask about neutral atom system, of course, as well. So we're thinking about new development in this front to address this issue. And so one capability we're developing, between Harvard, MIT, and collaborators is this continuous reloading of qubits and atoms. So here we only have this fixed number of qubits loaded. But with continuous reloading, we'll be able to have another reservoir that has a lot more qubits continuously and reload them. So as we lost some of the atoms by measurement, we can reload them and get them back into the computation again. And this also provides us fresh qubits as well. That's one way to resolve this. And also there are also other schemes that for now, when we measure the qubits, we actually lost them. But there are schemes that we don't necessarily need to lose the atoms when we do the measurement. And there's new development in the field as well that we can measure the qubits and retain the qubits without losing them.
I have a question for you, but then I would love to have Anette and Marcus add their perspective as well. I think, Shengtao, in your job, you work both on error correction, but also work with customers on actually implementing algorithm. Would you say that a certain error correction code is universally applicable to all algorithms, or would different problems force you or drive you to choose different error correction codes?
That's a good question. So our belief is that for at least for the near future, next 5 years or so, it's really critical to co-design the error correction code, the algorithm, and the hardware together. What that means, you cannot just give us an abstract error correction code and just implement, assuming we can implement on the hardware directly. There needs a lot of co-design between the error correction code and hardware for implementation, for layout, for specific hardware considerations, and also between error correction code and the application as well, because different error correction code have different native gate set, and that will have big implementations of how do you implement the algorithm, and is that particularly tailored to a certain application. And before we have this large scale fully fault tolerant device that we have fully abstract away, we need to consider all this co-design element that will be able to really push the frontier and able to get most out of our quantum computer in the near term.
And maybe Anette and then Marcus, do you have something to add to that perspective?
I mean, in general, I totally agree. So, I mean, probably on the very long run, we might end up with just one code for everything. You know, once we're at a stage where qubits are not expensive, where we can just, like current classical computers, just implement anything. But in the near term, I totally agree that I think there's a lot that you can get from really tailoring the algorithm to the hardware and also taking into account the code that you use. I mean, this is partially also what we do at Parity QC, to really try and not do everything with the same method, but really try to find out what's the most efficient way in each case.
And Marcus, did you see it the same way?
Yeah, I'm not so sure whether we will be working ever with one and only one code. I mean, the only approach I know is kind of with magic state injection, and it's not so clear that this will be the ultimate way of doing this. In my opinion, at least for the mid and near term, I would say, in my opinion, these color codes that you've also seen in Sheng Tao's talk and in part of my presentation are quite powerful because they allow you already to do a lot of gates, for instance, to the color codes, the Cliffords, and then you need one way to complement it with just one additional gate. And I think the interesting question over the next years will be whether these other new codes that people come up with, these quantum LDPC codes, which we've only kind of briefly alluded to in our presentations, even if they provide nice error correction properties, really of whether we find good ways of doing universal logic gates in these codes. I think this will, in my personal opinion, then determine a bit the faith of these codes, or whether we will be living kind of with a more qubit-hungry, nice and modular topological codes, be it 2D, be it 3D, that are modular, or whether we get to also for quantum computation. I think this will be the key, whether we get these other new codes, quantum LWC codes, actually to work there.
I have a question from the audience that I'd like to ask Anette and then go back to other topics. So Anette, the question is, what is special about encoding information in Schrödinger cat states? How can cat states be fault tolerant?
Right, yeah. I mean, I'm not the expert on cat qubits, of course. But so the thing we see, first of all, you have actually kind of error correction built in because you use an infinitely dimensional system to encode a qubit. So it's, in a sense, it's like other error corrections where you use many qubits to encode a qubit. Now you can use the whole harmonic oscillator. So that's where you get the redundancy from, that maybe encoding a qubit into something that's already just a two-level system doesn't give you. And then on these cat qubits, I mean, I guess I can't go too much into detail, but there's like, just by the way of defining these qubit states as these coherent states, there's a lot of ways of performing gates on the cat qubit that are not rotations in the Bloch sphere, but actually leave the Bloch sphere, get back in again. And this is kind of, it allows you to circumvent some no-go theorems on, for example, bias preserving gates, just because I have these more degrees of freedom that I can use to actually do something.
Sheng Tao mentioned in his presentation several times collaborations that Quera has with Harvard, MIT, and others. And Marcus, you are also in the university, and I think you also collaborate with several companies. How important is that industry academic collaboration in your mind?
Yeah, I can perhaps start.
Please.
Yeah,
Yeah.
I'm working. I'm mostly, I have to say, with academic partners, but also a little bit with company spin-outs. Of course, this kind of customer perspective, and to understand, okay, what can you really get out of your device, kind of puts your feet a bit onto the ground. But I also like to think about a little bit more the long term, mid and long term perspectives. What I definitely find very, very important is to collaborate as a theorist with experimentalists. Yeah, I think this is super important. I mean, not only to get new ideas, but also really understand what the challenges are and think about schemes of how to overcome them.
And if I can ask you another question, Marcus, and then maybe Anette and Shengtao. What are the current research frontiers in quantum error correction? Where if you were sort of going into this field just as a postdoc, what would you focus on as sort of exciting areas that still have a lot of work to be done in?
Well, I think, okay, there are several areas. We have already mentioned a few. I think developing new codes is very interesting and super important and timely. What I personally also think, there are still things to be understood on the fundamental error correction power of codes. This goes in the direction of understanding these quantum error correction codes and their relations to statistical physics, which is very, very interesting to really understand independently of suboptimal decoders what really the best is that you can expect of certain codes. And then these co-design questions are something that I like, to have these hardware platforms in mind. I enjoy a lot working with the different hardware platforms and their capabilities. And as also Shengtao mentioned already, you can't think about running certain codes, algorithms, schemes without kind of having hardware in mind. And I think bringing these things together in an optimized way is something that is certainly very valuable. And I think there's still a lot to be done in that direction.
And Shengtao, your perspective?
I really like to highlight the last thing Marcus just said as well, just co-design idea. And for new people coming into the field, quantum error correction is no longer just theory working abstract. It was in the past, 10 years ago, but now it's really, it works in the experiments as well. So one of the frontiers is really to co-design the error correction code with the hardware and think about, bias noise and, for the particular bias noise, what kind of error correction code you can do. And also for particular architecture, can you make use of the, long-range connectivity? Can you make use of the reconfigurable atom and ion architecture to implement error correction code, this LDPC code and other new code as well. So that will be really kind of one of the key frontiers. For other things, if I may complement as well, of course, new error correction code, and with that, thinking about for this LDPC code, we still don't have a complete and clear picture of implementing universal gates on it. And how do we do gates on it? That's still a kind of a open question in the field. And in general, the goal of some of this development is also to reduce the space-time overhead as well. So as we know, error correction is very costly. If we want to reduce the error rate to 10 to the minus 15, we need a huge number of physical qubits. How do we reduce the space-time overhead? This is also one of the work I just talked about. We try to reduce the number by this D factor, and that already gave a huge speed up in terms of a space-time saving. And there's might be other new innovations and ideas one can come up in this direction as well. And then decoding. There's a lot of challenges. How do we decode fast with good performance? There's just so much to be done in this error correction research field.
And it's interesting, Annette, that I heard that you had the company has transitioned from focusing on implementing optimization problems to actually realizing that what you have done is very useful for quantum for error correction. What do you see as the research frontiers that your team is working on?
Yeah, I must admit the most fun part is, of course, the developing a new code. But I think the thing that's maybe really missing the most, and that maybe also needs much more work, because maybe it's not as fascinated as other things, is really developing decoders and doing proper research estimations. Because, you can have a nice code with cool properties, but then that tells you nothing in the end of how the actual algorithm will run on it. So, this is just the heavy lifting that needs to be done. That's just like dry calculations. But this is what we, I think, really need in the end to see what code we should use or which codes we should combine or where we can improve something. And especially also on the decoders, this is even something I think for a lot of codes we still actually need to develop really well working decoders that can also implement it in real time. There's nice ideas, there's some decoders that work well, but not every decoder works equally well on every code, and not every decoder is equally efficient, or, for example, can be implemented on FPGAs or other like local classical coprocessors. So I think this is we just at some point have to accept that we also have to do these kind of parts of the work to get where we want to be.
I have a question for Xingtao, and then maybe I want to talk about that transition that Marcus mentioned from the physical qubit era to the logical qubit era, sort of the dawn of a new era. Xingtao, you mentioned transversal gates and different error correction codes. Can you do any gate transversally? Or does it depend on the code, or how does that work?
The answer is no. In all the theorem Marcus showed in his slide, so you cannot do universal gate transversally. So that means, it's always, there's no free lunch. You can do some gates transversally, but not all of the universal gates. So with that, there comes a lot of room for innovation as well. So for example, color code, which Marcus mentioned, is one of the very nice code. You can do Clifford gates transversally, but non-Clifford gate you have to do it in some other ways, and this code switching, and it's really nice implementation idea. So that and depending on the algorithm, of course, depending on the application, depending on what you like to achieve, whether it's chemistry, whether it's optimization, and that may require different native gate set. And with that requirement, we need to find like what kind of error correction code will be most suitable for this. And then, hopefully most of the gates we can implement transversally and couple with some other gate that we implement in other ways.
And so that speaks, I think, to what you described as code design. So if I want to solve a problem and I want to use a certain quantum algorithm, then that algorithm could be implemented in different gates, and the choice of gates depends on what code I'm using or what error correction. And so you're basically working at all levels of the stack at once, as opposed to, oh, here's the code, just compile it and run it on your hardware. Is that correct?
That's correct. And I believe that's the right approach for this time of the field. And of course, we can abstract away slowly. And at some point, we can just, don't care about the code and just customer give us, this is the algorithm we want to implement, but just implement in the best way. We provide certain levels of that, but eventually to get most of the hardware in the next 5 years, we need to co-design the entire stack.
So since you guys have shown some beautiful slides, I wanted to show 3 slides of my own and then just a little bit about Quera, and then use that to go into this discussion about the transition, if I may. So very briefly, so Quera is based in Boston. We do computers that are based on neutral atoms. We believe we are the leader in neutral atom computers. One reason we believe that is that in November of 22, we launched our first neutral atom computer on Amazon Bracket. So it's available for worldwide use for more than 1.5 years now, 130 hours a week. So pretty much the entire week you can submit jobs and get them executed. We've mentioned that we are in Boston, close both physically and also sort of mentally to Harvard and MIT. There's a lot of collaboration going back and forth. Some of the Harvard and MIT experiments use equipment that was built or designed at Quera. And of course, we try to bring a lot of the academic innovations from Harvard and MIT into the product. Team is growing. We're hiring. And about 6 months ago, we published our roadmap for quantum computing, and basically said, today we have a 256 physical qubit computer that works in analog mode. Maybe Xingtao, you can talk about that a little bit soon. This year, we're making available to early customers a computer that has at least 256 physical qubits, but most importantly, at least 10 logical qubits. That will be followed in 25 by a computer with about 3,000 physical qubits and 30 logical qubits. And then ultimately, in 26, more than 10,000 physical qubits and about 100 logical qubits. And obviously, with 100 logical qubits, we're exceeding the simulation limits of classical supercomputers. So we're really excited about stepping into this area of the unknown, where we can say the results are correct, but we don't know what is it that you're exactly going to get. Maybe our favorite quote of last year was one from Professor Preskill that looked at the roadmap and said, it's ambitious but not crazy. So if he said it was ambitious and crazy, we would be worried. If he said it's not ambitious enough, we would also be worried. But ambitious and not crazy is a good combination for us. So I'm curious to ask you, for instance, Marcus, if you had access to a computer next year with, say, 3,000 physical qubits and 30 logical qubits, and you wanted to run an algorithm, what would you choose? Would you run it on the logical qubits, or would you use error suppression, error mitigation, or other approaches to run it on the physical qubits?
I think I would run it on logical qubits, yeah, because I think when I've seen also in the experiments that were done there by Bluestein and collaborators, is that this, even if you do not fully fledged error correction yet, simply this ability, as soon as you start to work with logical qubits and you can detect errors, kind of sort out the bad runs, keep only the good ones, this allows you for an improvement of the algorithmic fidelity, let's say. So I think this is more promising, not meaning that you should not do any kind of error suppression on top, decoherence-free subspaces and etc. But I think I would go with logical qubits. The only remark I also have about this ambitious and perhaps not completely crazy roadmap, I also think it's not crazy, is that if you have, let's say, 100 logical qubits, one has to be a little bit careful. It does not automatically mean that you can run quantum algorithms that you cannot classically simulate anymore, because they're essentially facing also this problem that, of course, the non-Clifford gates are very hard, and they make the computation hard. And we've only a very discrete set of gate operations, so to say. One has to see, what will be really the depth also of this algorithm, how many kind of non-trivial non-Clifford gates one can do. And I think on this, it depends on whether we can, on the midterm, see interesting applications. If we think, for instance, about simulating time dynamics in a Trotter type version of many body dynamics, then one has to see how efficiently this really works, because we cannot do, in contrast to single physical qubits where we can do little rotations here and there, or little Trotter steps. On the logical qubits, you can only do kind of these big steps, either Clifford or 45 degrees. And then one really has to see kind of how complex and deep the algorithms will be. But I'm fully convinced that this will be the mid and long-term way to go, clearly. Question is how far we get there.
And Annette, if a customer came to you and said, I need you to design an algorithm to use on this hypothetical computer with 3,000 physical qubits and 30 logical qubits. By the way, the ratio, of course, depends on the encoding scheme that you use and the code distance and so on. What would you choose?
I mean, of course, I would first try to run the Parity code on this hardware. But I think also, like, on such a device, of course, depending on the error rate, if you run something on logical qubits, first of all, it won't be any big algorithm, so you won't really get anything that you can't classically simulate in terms of the logical effect of the circuit. Of course, you can do a lot of simulations of how well the error correction works and so on, which can be interesting. But I think also it might still be worth trying out some maybe semi-physical, so like maybe error mitigated or just partially error corrected algorithms. For example, with the Parity architecture, maybe some optimization algorithms that still require only really short depth, but can really benefit from a lot of physical qubits. So I would also go more in this direction to see if one can still do something on the actual qubits. Of course, depends on the error rate.
Very good. I want to present to you a question from the audience, and any one of you is welcome to answer it. The question was, could you please explain error correction benefits of using Schrödinger cat states as compared to Gotsman, Kitaev, Preskill states, or vice versa?
I assume this is for me again then, or
you're welcome to answer it.
I mean, okay, I can. Let's say I can tell you the benefits why we prefer them. I think both have their benefits, so I can only say why for the Parity code we prefer cat qubits, because for the cat qubits you get this kind of exponential suppression of one error at only linear increase of the other error. Whereas I think in the GKP qubits, as far as I'm aware, it's a little bit harder to I mean, you can still squeeze the things and get a noise bias, but I think the kind of biasing strength of like one suppression and the other increase is much better on cat qubits. And also these kind of options of performing bias preserving gates are really nicely worked out on cat qubits. I mean, I'm very curious to see what, for example, Amazon comes up with on GKP qubit or anyone else, but so far I'm not seeing as many really useful capabilities also in terms of fault tolerant gates, or at least bias preserving gates on GKP qubits.
We're about 6 months away from Christmas. What would you like your quantum error correction Christmas present to be? Marcus, maybe you go first, and then Shengtao, and then Annette.
I think, I mean, what will be exciting is to see the first, repeated error-corrected universal logical gates. Yeah, this I think, I don't know whether it will happen by Christmas or a bit later, but this will be, I think, definitely the next steps. And then what I find technologically very interesting is to, in many platforms, neutral atoms, but also in ions or superconducting qubits, to kind of keep this machine running for longer and longer, to bring in fresh qubits. Sounds a bit boring, but this is, I think, really what one needs if you want to sustain these things. And I think there's at the moment a lot of progress in doing this, suppressing, detecting, correcting leakage errors, bringing in lost atoms, keeping, your registers fully filled, and reincorporating lost qubits. I think these will be very, very exciting steps to see.
And Shengtao, what would you like for Christmas?
Yeah, my Christmas gift, the one I want to get, is a error-corrected Lego set. Just joking. So we have a Quora Lego set of our quantum computers. So if I have an error-corrected one, that would be a wonderful gift. So joking aside, I would actually say the same thing as Marcus. Repeated error correction, and that's a large scale. That's something will be amazing to have by Christmas. And for neutral atoms specifically, there's a lot of technological advancement one can realize as well. Some of the things I mentioned before. Bringing fresh qubits in, with this continuous reloading of atoms that show that we can, as we lose atoms and qubits, we can continue, replenish them, and then this with measurements that does not result in losing the atoms, and that's also, in relation to keeping the atoms and in this continuous feed-forward fashion. So yeah, on the technology side, I'm really excited about neutral atom system, and also, I'm also excited about other platforms and seeing advancement for travel ion system, for superconducting qubits. There's really, a very exciting time for the field.
And Shengtao, since you mentioned the Lego set, I couldn't resist but showing it. This is over 2,100 pieces of our 2024 computer, and you can actually win one. We have a survey on our website in the blog area. And 1 out of every 100 participants will win this. It's not AI generated. This is a real set. We've built some of them at Quora. So we build both real quantum computers as well as Lego ones. Annette, other than this Lego set, what would you like for Christmas?
I mean, as the more realistic wishes are already out, maybe I'll just be a little bit crazy and ambitious now and say I wish, of course, to see an actual useful algorithm implemented fault tolerantly. So not just an algorithm chosen to be easy on this code or to kind of, work out in this particular case, but an algorithm that actually comes from an actual use and not just from what can I do in this code. But I mean, I realize that this is maybe a long shot, and I don't know how lucky I'll be this Christmas with that wish.
Yes, and I think that some organization like XPRIZE that are offering up to almost $5 million for development of such algorithm. I think they're looking at a 3-year time scale to win. But who knows? Maybe they can give out the money sooner. And so,
if I may jump in,
please.
Perhaps one other thing that I would find interesting is if by Christmas something has come up that we are not aware of. Like a new approach. I think we should also not kind of only focus on the standard way of doing things. Parity QC architecture is, of course, one way. I also personally think that thinking about autonomous, self-sustained quantum error correction is an idea. There's still the open question of whether we can build self-correcting quantum memories, which many people have attempted. So if something like that comes up and works, this will be, I think, a bigger change than kind of the things that we've mentioned so far. But of course, it's very hard to kind of say it will be that thing. And that is also answering partially what you asked before. If you're a postdoc in the field, then you might also want to tackle these type of questions.
And the last question today, which is usually the last question I ask my guests on the Superposition Guys podcast, maybe to Annette and then Shengtao and then Marcus. If you could have dinner, it's a hypothetical question, of course. If you could have dinner with one of the quantum greats, dead or alive, but not both dead and alive, dead or alive, who would that be?
Yeah, that reminds me of, like, we sometimes have this kind of science crush question of, like, who are you most fascinated by? I think I don't know if everyone it's maybe not the name that everyone know, but I am really fascinated, and I also got like almost educated a lot by Fowler, like Austin Fowler, I think with Google now or with the team, just like because it's such a like I feel like everything came out of his ideas in terms of surface code and how you can do everything, how you can evolve everything, and of course also this. I think this is the paper that I learned quantum error correction for, this surface code paper that everyone cites now. So for me, I think this is one of the persons that I admire most in terms of quantum error correction these days.
In Shengtao, who is your dinner guest?
Yeah, my answer might be, I think many people would choose the same answer. I would like to have a dinner with Richard Feynman. The reason being, I want to ask him, what does he think about the progress of the field now? And he proposed using quantum computers to do quantum simulation, and that's part of my field as well. Before doing this quantum computing stuff, I'm more focused on quantum simulation with neutral atom trivalent system as well. So this is still one of the big areas for quantum computer really to do quantum simulation, solving material problems, solving chemistry problems, and what does he think about the current field of development, and how far are we, based on the current development, how far are we from reaching the goal of finding useful applications of quantum simulation?
And Marcus, before you answer, I want to tell a little story. I had the opportunity to ask Professor Preskill that question about dinner. And I told him that most everyone says Feynman. And he says, no, I've had plenty of dinners with Feynman because he was his student. And then, of course, then he came back and said, actually, I would like to have another dinner with him to see how he thinks about today's progress and how some of his predictions came true or not. But who would be your dinner guest, Marcus?
I don't know who my dinner guest would be, but in April I was lucky to have lunch actually when I organized the workshop at the Simons Institute in Berkeley with Peter Shor, right? And Peter Shor, I mean, he not only kickstarted the field of quantum computation as a whole with his algorithm, of course, but we also shouldn't forget that he is also one of the pioneers who thought about the first quantum error correcting codes. So that was a very pleasant and fascinating encounter. And I'm happy if I just kind of had this lunch this year. And with these pioneers of quantum computation and quantum error correction.
And Peter Shor is also indirectly responsible for a lot of the commercial interest in quantum because Shor's algorithm kind of both scared and excited people about the opportunities in quantum, and I think that generated a lot of investments. So with that, Zainab, I would like to turn it back to you. I think we've answered all the questions and covered many, many topics today. So thank you very much for organizing this. And thank you, of course, for our panelists for being so patient with me and with our audience.
Thank you so much, Yuval. Thank you for, first of all, offering to have this meeting and also this moderation and very interesting questions. We really enjoyed it. And I would also thank our speakers for their very fascinating talks and also this roundtable discussion. I'm sure we all enjoyed it, and also our audiences and also the ones that are seeing us on YouTube. And with that, I would say that we have reached the end of this quantum leadership session, and we wish to have you all again in the other leadership sessions of QBN this year. And I wish you a nice evening and the rest of the week.
Thank you very much.
Thank you again. Thank you.
Thank you very much.
Bye,
Thank you all.
everybody. Bye.
Bye-bye.